This lecture is about residual analysis. As you've seen in the previous lectures, it's quite important for us to be able to determine whether a sequence is deemed to be white or not. For instance, when we are looking at some kind of measurement that we construct a model for, and we want to deem whether the resulting residual, the modeling residual, is white. We want to then to be able to see whether that there is some further structure in the residual that we can exploit, and that in this sense we can go back and improve our model so that there is no further structures to be able to improve it. There's several different ways of doing that. The first and easiest one is just to plot the ACF and PACF and eyeball the result and see whether everything is inside the confidence interval and therefore deemed to be white. However, this can be quite tricky. So say what I have something like this. Notice that I have several peaks that are just outside the confidence interval, but they're just slightly outside. So is this a white sequence, or is it just sort of borderline white or whatever? In general, we tend to try and say, well, maybe it is white, maybe it is not, and we'll just test it and see whether we can get away with it. But you would like to have a little bit more confidence to be able to do that. And the way to be able to get that confidence is to use statistical tests. You're basically making a hypothesis test. You say, this is a white sequence, and then you test that hypothesis versus the probability distribution of that, test the statistic that you're driving, and then you are getting a conclusion, say with 95% confidence interval, this is a white sequence. There are also two other tests. You can check whether the periodogram is flat. I mean, from a power spectral density perspective, you want the power spectral to be flat, like this, if it's a white noise. Obviously, it's not going to be that. It's going to be something wiggly, as you know. But the question is then, how wiggly is it? Is it sufficiently flat to be able to be deemed to be a white sequence? That is the cumulative periodogram test we'll talk about shortly. You can also test the number of sign changes the sequence has. Remember that if it's a white noise, you're basically bouncing up and down, having infinitely many frequencies in it. So you basically should swap signs every single sample. And if the number of sign changes is reasonable given the sequence, you can then say that this is deemed to be white. An important aspect is that all the statistical tests will make, they depend on the assumption that the autocorrelation function is Gaussian distributed. So you will need to remember to check whether that is true or not. If it is not perfectly Gaussian, you will have to be sort of flexible in your interpretation of the result, and maybe you cannot trust them at all. So the third thing to do is just to plot the ACF and the PACF and see whether this is statistically significantly inside the confidence interval. Remember, everything that is inside the confidence here, we deem that to be statistically not different from zero. So this is all zero. So the question is whether these things that are just outside are just slightly outside, or whether they are just the 1 in 20 that's sort of almost inside. One way to do that is to sum up the square of the autocorrelation function estimates. Remember that if they are asymptotically normal distribution, if you square them, they should be chi-square distributed. So you can test whether the sum of them, each one of these will be chi-square distributed, and the sum of them should then be a chi-square distribution of k degrees of freedom, and you can therefore test whether the sum of the k ACF components are significantly different from zero or not. K here is the degrees of freedom. You typically pick that as a low number, say 10 to 25 or something, depending on your data length. You do not take too many, you don't have too few, because you want to have a bit of an averaging, but you also know that the higher order lags are going to be quite unreliable, so you want to make sure that you stay well away from those. The resulting test is called a Box-Pierce Q test, and you test then the statistics whether the statistic Q that you computed is comparatively distributed as the chi-square distribution of k degrees of freedom that you expect it to be if it's a white noise. And remember, this is if the ACF is then Gaussian distributed. It's not the data itself that is you asking whether that is Gaussian distributed. You ask if the ACF is Gaussian distributed for this to be reliable, because you are using the square of the ACF, and you are saying that since the ACF is Gaussian distributed, the square of them will be chi-square, and therefore the test will be chi-square. So you cannot really check if the data is Gaussian or not. It's the ACF that you need to check. Here are some further tests. The Box-Pierce tests tend to be around reliable when you have small amount of data, so you tend to use the Young Box-Pierce Q statistic, and then what you do is you scale each of the ACFs like this, and then you scale this, and it will still be chi-square distributed. This is normally quite a good test. You can also use the squared of the residual, and then squaring the ACF of the squared residual, then you get the McLeod-Lee test. This is generally not very reliable, so because it depends very strongly on the Gaussian distribution assumption. If your data is not Gaussian distributed well enough, this will fail miserably, and you will see that in the Gaussian test, you will very often have this fail. I would not trust this test. I bring it in here just so that you can see that some tests might be very strongly depending on the assumptions, whereas others are more flexible. This is not a robust test, so it should not be trusted. One of the better tests is the Monty test, when you look instead on the PACF, but otherwise follow the same principle of this Young Box-Pierce test. All of these tests are available in MATLAB, so we provided functions for you can test it. As I mentioned, you can also test the periodogram to see whether it's sufficiently flat, and what you do then is that you sum up the periodogram up to a certain frequency, so I have the wiggling part and I'll sum it up to this point, and if it is flat, up to this point, it should be a straight line. So you expect it to be a straight line like this. But if there are some significant things going on, you will have bounces out of it. So you should expect something like this if it's a white noise sequence, whereas this here, it's a not white sequence. And you can see that I'm now differentiating from the diagonal line that I'm expecting it to have. The confidence intervals here are given by this table, so I can just look it up. There's a function plot compare that you can use and generate this plot automatically. You can also check the number of sign changes. This should be a Bernoulli distribution. If you have enough data points, this will be well approximated as being normal distributed. And you can do the same test by calling this function count sign changes, basically assuming that if it is a white sequence, it should be changing about every second time. And so if it changes less than that, it's not deemed to be white. All of these tests are gathered up in a function called whiteness test. So if you call the whiteness test, it will compute all of them. You should be aware that you shouldn't do multiple tests and then you see if you can pass one single one of them. I mean, if you do 20 tests, you will pass one of them just because of the 95 confidence interval. So you should pick one, for instance, the Monty test or the Ljungbox-Pierce, and then trust that. So when calling the whiteness test, it is more to show you how they differ and that you can get different opinions by the different tests, and some of them are more reliable or not. But in general, if you pass one of these tests, you should feel fairly confident that your data sequence is roughly white. If you pass more than one, you should feel more confident in that. But again, trust one. I would suggest the Monty test, which is a very good one. Finally, the issue of normality is relevant here. Remember that the ACF and the PACF, the tests on those assume that these sequences are normal distributed. So it's not the data again, it is the ACF and the PACF that's supposed to be normal distributed. So you need to have a statistical test to tell whether these are normal distributed or not. What you do then is you test the kurtosis and the skewness. So the skewness is how tilted the PDF is, and the kurtosis is how peaky it is. And there's two classical tests. One is the Jack-Barrett test, which is formed like this, and you assume then if it's a Gaussian, your skewness should be 0 and your kurtosis should be 3, and you basically test if that is the case. And there's a test for that called JV test. There's also a more advanced test, which is the Agostino-Pearson K2 test, which is often better if you have small amount of data, and this is implemented in the Agostino K2 test you can call. A good idea is also to use the norm plot, or the one that we provide, norm plot NT distribution, which checks also for the T distribution. Then you should get something like looking like this, where the blue line is the ideal normal distribution, and you see here that the tails are slightly heavy on the side. This is always basically going to happen because of your finite data results. And you want to make sure that this is not looking something like this, that you have a bounce in the middle. The T distribution then will instead follow something like this, so you can check whether your data is more reasonably described as T distributed, and you will see that this is quite common in many forms of data sets, that the T distribution describes the data well. What should you then do if you deem that your ACF is then T distributed instead of normal distributed? Well, first of all, you cannot really trust your test, but that doesn't mean that they're completely wrong. You can just not assume that they are chi-square distributed. They will follow another distribution, so you can basically do the derivation and see what is the distribution of a T distribution squared, but that's going to be a pain. So basically you want to make the conclusion that if it is not perfectly normal distributed, your tests are not going to be reliable. So you should trust them less. So you should see them as indications whether something is white, but not as something as truly saying that it is white or not, meaning that you should not trust them fully.